Amplifier Evolution.
Sure.
Yana,
yeah.
you want to take us through this?
Let's do it. Yeah. So back in the 1940s and 1950s, when television was becoming so popular, it was really difficult for those cities around outside the rural areas to get the signals. So some manufacturers are starting to develop some products to address this issue, and one of those products was amplifiers. So the first ones, that one of the first generations, they supported around 12 channels, and they consisted of a technology called twin lead wire, and they were based on tube amplifiers. This had a really simple circuit, and it was a bandwidth between 54 and 212 megahertz, and they only supported the downstream direction. By the early 1970s, the cable television upgraded those twin lead wire amplifiers to a higher technology, and it was called the solid state actives. And those was introduced to support higher bandwidths, up to 330 and then 450 megahertz. But then in the 70s, actives continued to evolve, and then the first standard package of semiconductors hybrids was introduced, and it was known as the SOT115J. This package was a big change on amplifier evolution because it helped operate a narrow band with short, not that many blocks, but it helps them to support two systems. So we introduced the upstream. These early two-way systems were from 5 to 30 megahertz, known as the sub-split or low split, and then from 54 to 450 on the downstream. But as demand for capacity increased in the 1990s, amplifiers with new technology were introduced to improve performance, and we increased parameters like frequency bandwidth, operational gain, and output levels to support high-speed internet services in longer distances. Then in the 2000s, with the introduction of digital compression, the signals advanced, and the semiconductor industry help amplifiers to improve even more. These advancements in semiconductors have been allowing us, the vendors and the operators, to support higher reliable services, and it has created a next generation of amplifiers called smart amplifiers, which use everything electronic, and then they're going to have the auto alignment control. The next one. So as far as the configuration, on the forward path, some of the early hybrid amplifiers only have a push-pull stage, and for a brief period, around 450 to 550 megahertz amplifiers included a feed-forward stage. This technology had bandwidth limitations, and it never developed beyond 625 megahertz. Then, as the bandwidth and performance requirement increased, the push-pull circuit evolved to a pilot hybrid gain block and introduced significant improvements on performance and higher output levels. The output stage today, as we know it, is a doubler block, and it uses a driver as a mid-stage block to support high output levels that are required to overcome the coax attenuation at the higher frequencies. Recently, a pre-stage low noise amplifier has been introduced with low noise figure to support those even higher levels that we need, while increasing the performance as well. On the return configuration, the bandwidth has increased at a lower scale. So the stages started with 1, then the 1.2s, that as we know them today have 2 stages, and then as we go through ultra high split, it's going to require an extra stage.
I think this is important to spend a little bit of time on as you talk through the evolution of amplifiers into some of today's, even though they're higher quality components, having more stages of amplification to achieve the higher gain to support higher frequencies also brings with it some risk, right? I think we'll talk more about that later, but some of today's amplifiers have 4 forward gain stages and 2, to your point, in the future, maybe 3 return gain stages. So that poses some real challenges if they're not set up properly.
Right. Yeah, as we know, the hybrids are getting more complicated. Also, they are implementing stages in between the vendors, EQs and pads to be able to keep those stages happy. So at the output, we keep performance. So we need to be really diligent on understanding the amplifier and working with the vendors to make sure that we are setting them properly, and with the operations teams, because not all the HFCs are the same. So, and not all the amplifiers are the same. So we need to be careful on how we set those levels, and we will get in more detail on the next slides. On this one, we just wanted to highlight some the evolution of the semiconductors. So the first generation of the hybrids used on the output stage were BJT, or bipolar junction transistors, and these were used on analog amplifiers. The performance of these hybrids met the requirements needed back then, and they were used between 450, 550, and 750 megahertz amplifiers. In the 90s, the gas technology die was introduced, and it was able to support 860 amplifiers. Then the gas hybrids demonstrated questionable performance advantage versus the bipolar. So for the time, at that time, the die was kind of improved again in the early 2000s, and this started to be implemented in the 1 gig amplifiers. Then the next generation of the hybrid amplifiers was introduced in 2008 when GaN was adopted by the cable industry. These the power doubler gain blocks that provide delivery of high power and high frequency can also withstand really high temperatures. GaN-based amplifiers match the performance of the gas and even better the BJT, and they provide lower power consumption. Also, they perform way better. And this technology has been implemented mostly on the 1.2s and future 1.8 amplifiers. As we increase the bandwidth, amplifiers need to operate at higher frequencies, so we need to be really cognizant of amplifier TCP limitations, or total composite power, for unexpected performance. So we can see in this graph that in 1.2 amplifiers with 69 TCP, now we're pushing that to 75 in the 1.8s, and it's really close to the compression region of the semiconductor. For the 1.8 and the future 1.8, we need to be real careful on design, on following the design prints, or making sure that we know the dry levels of the amplifier, like where Mike is going to touch on later, to avoid operating these amplifiers in the crashing region.
So we see that difference between 69 total composite power and 75, and you're like, that's only 6 dB. Well, 6 dB is actually a lot when you're talking about total composite power, right?
Right.
So that's really important. Well, we talk a lot about total composite power today because it really is important to the overall performance and capability of the amplifiers. So good stuff.
Mm-hmm. On the upstream, there's not been a lot of changes. It's mostly following the progressive path of the forward. And as we can see, it's being marked by the same technologies. And we're now introducing ultra high split that is probably going to require the use of GaN technology.
Oh, hey everyone. Mike Odell from the Penn Ohio SCTE. That wraps up another episode. I hope you enjoyed today's content. If you have comments on content you'd like to see, add those to the comments below. And for more content like this, don't forget to like and subscribe.